Hello dear learners, once again welcome back to the new video. Today again we are dealing with the same topic, that is the Clapeyron's three moment theorem. Now today we are going to consider a continuous beam having two spans which has been imposed with the point load. So here we can see that we are having a continuous beam ABC which has been imposed with a point load exactly at the center of the first span, and the distances are been mentioned from A 2 meter, another 2 meter span, and a second span of 6 meter. In this problem we are required to find out the reactions as well as we have to construct the shear force and the bending moment diagram. Now here in this figure 2 you can see what we did. We have drawn the free bending moment diagram, in which we know as a standard case simply supported beam with a point load at the center, its free bending moment is equal to WL1 by 4, and putting the values we are getting that bending moment equal to 40 kilonewton meter. Now the first job, as we know, we are dealing with the Clapeyron's theorem. So first step is to apply the three moment theorem for this particular spans. Now after application we know equation number 4, that is MAL1 plus 2MB in the bracket L1 plus L2 plus MCL2 is equal to 6A1 x1 divided by L1 plus 6A2 x2 by L2. Now here certain parameters are required such as MA, MB, MC, A1 and x1. L1 and L2 are already given. We know this being a simply supported continuous beam, the supports are simple supports with the hinge and the rollers at B and C. So here total reactions, if I count down, horizontal reaction, vertical reaction at A, B one reaction vertical, and at C there is one vertical reaction. So overall there are four unknowns present in this. So this is again a statically indeterminate structure. Now to find out that, we are applying the Clapeyron's theorem, and this is what we have a governing equation as a Clapeyron's theorem. Now let us work out the various values. MA being a simple support on the extreme end, similarly point C or support C is again a extreme support on the right hand side. Both are simple supports. As far as this B point is concerned, there is a partial fixicity where there will be certain moment occurring at this particular point. Is it okay? So here we conclude first thing that MA and MC should be equal to 0, being extreme and simple supports. So MA is equal to MC is equal to 0. Now as far as this A1 x1 and A2 x2 are concerned, so A1 x1 are related with the first span and its free bending moment. So A1 area of this triangle, which is equal to half base into height. Base is 2 4 and height is the 40 altitude. Is it okay? So half 4 into 40 is equal to 80. Now as far as x1 is concerned, x1 is again half of this particular triangle, that is x1 is equal to 4 by 2 equal to 2. As far as A2 and x2 are concerned, both are equal to 0 because there is no any loading imposed on this second span BC. So A2 as well as x2 will be equal to 0. And already we have concluded MAA is equal to 0 and MC is equal to 0, being they are the extreme simple supports. So putting back all these values of A1 x1, A2 x2 and MA MC in this ruling equation, governing equation of Clapeyron's theorem, we are getting a new equation 0, 2MB in the bracket 4 plus 6 plus 0, 6 into 80 into 2 by 4 plus 0 is equal to 0. Is it okay? Now simplifying that, you will be getting a one unknown, that is MB is equal to 10 kilonewton meter. So this is sagging, so it is taken as a positive. So this is what we have as a first job. Moving ahead, the second job is to find out the support reaction, for which we will see first span of AB. Here this is A support and this is B support. By mistake it is B and C, so it is A and B support. So here whatever we know are being shown. So what is known to you? MA is equal to 0 and MB is equal to 12, already found out in the earlier slide. RA we don't know, RB also we don't know, and the distances are 2 and 2 from the center. Is it okay? Now applying the simple condition of equilibrium, sigma m about point B is equal to 0. This is B, not C. So taking a moment about point B, so here what we have, RB into perpendicular distance 4, MA is equal to 0, 40 into 2 plus MB is equal to 0. So putting that and simplifying, we are getting RA is equal to 7, because in this particular figure we can see only one unknown while taking a moment about point B. Similarly, second span we can work out for, that is span BC. So again we are going to do the same. We are going to take a moment about point B, and whatever we know we are going to take the moment of everything. So MB is already 12, MC is 0. This is what we have, RC. So RC into perpendicular distance, it is forming anti-clockwise, so minus RC into 6, this equal to 12. It is anti-clockwise, so minus 12, and as far as this MC is concerned, it is equal to 0. So putting all this in this equation, you will be getting a unknown, that is RC equal to minus 2. So here the answer is coming out to be minus. That means my assumption is wrong. It's not acting vertically upward, it is vertically acting downward. So this is how we have found out the second unknown, RC. So in order to find out the last unknown, RB, now you can see here most of the unknowns are been already found out. Now I can take a whole beam and I will be applying a basic condition of equilibrium, sigma Fy is equal to 0. So plus RA plus RB minus 2, that is minus RC minus 40 is equal to 0. So simplifying that, you will be getting the third unknown, that is RB is equal to 25. Now here there were three unknowns, RA, RB and RC, all are being found out in this particular fashion. Is it okay? Now as far as this horizontal reaction at A is concerned, as there is no any horizontal force acting, as there is no any unbalanced force acting, or we can say there is no any active force in horizontal direction, so there is no any reactive force in the horizontal direction. So obviously HA is equal to 0. So this is how we have found out all the unknowns. HA is equal to 0 because no unbalanced force acting on the beam in the horizontal direction. RA, RB and RC are also found out. Now the third job is to construct the shear force and the bending moment diagram. Here I have compiled all the unknowns which are being found out by the analysis of the continuous beam by the application of Clapeyron's theorem. Now let us construct the various diagrams one by one. So we know this is a original beam, original beam. Next diagram we have to construct as usual what we used to do in the shear force and the bending moment diagram. So I have constructed the shear force diagram. Next I have drawn the free bending moment diagram as already shown in the first slide. Then I have constructed the fixed moment diagram. So here I have shown you here MA is equal to 0, MC is equal to 0 and MB is equal to 12. Is it okay? For span AB as well as for span BC, MB is equal to 12, only with the difference when it is span AB it is anti-clockwise, when it is span BC it is for span AB it is clockwise and for the another one it is anti-clockwise. So after working out these values, yet we are not in a position to get what is the resultant moment. For that resultant moment we have to superimpose the two bending moment diagram. So I have superimposed the free bending moment as well as fixed bending moment diagram one above the other, and as I have told you earlier, this inclined line and this inclined line will be acting as a new axis, which we have already called it as a neutral axis, on which the bending moments are 0. Below that are the negative bending moment and above that are the positive bending moment. So here we can see I have worked out the positive resultant bending moment by just simply making the difference between two. If this is 12 at this end, so exactly at the center this will be 6. So ultimately 40 minus 6 is equal to 34 kilonewton meter. So this is what is the resultant bending moment acting on this particular beam, which can be further taken for the further analysis or design of that particular continuous beam. So this is how we have to work out the various unknowns first, then we have to work out the shear force and the bending moment diagram, and then at last we have to superimpose the two bending moment diagram one above the other, and we have to find out the resultant bending moment acting on that continuous beam. So this is what is the normal procedure which is to be adopted, may it be any case for any spans. Here we have considered only two spans, it can be n number of spans, but every time we have to consider two consecutive spans. If there are n number of spans, so take two consecutive spans at a time and do the same analysis. You will be getting the various unknown present into that particular system. So this is what we have for today. In the next class we shall be dealing with the again analysis of the continuous beam, in which we are going to consider one end to be as a fixed end and rest of the beam is going to be the continuous. This is again an interesting article to be learned from the analysis of the continuous beam. So this is what we have for today. Thank you very much.